Good afternoon, everyone. It is my honor and absolute pleasure to talk about the speakers today of today's Samvad talk on application of graph theory for spectrum allocation. So this is a classical example of marriage between two diverse disciplines. And of course, the professors are going to talk more about it in detail. And I'm very excited about it too. So Professor Jyotsna Bapat received her Ph.D. from Penn State University prior to joining IIIT Bangalore. She has worked as an assistant professor at Fairleigh, Dickinson University and Lucent Technologies in New Jersey. Her areas of interest span from Massive MIMO in 5G and beyond, network slicing, zero-touch networks, and security in IoT systems. Currently, she leads the Networking and Communication Research Lab at IIIT Bangalore. Professor Pradeesha did her PhD from Indian Institute of Science, Bangalore. Her research interests are broadly in theoretical computer science and specifically in computational and combinatorial problems in geometry. She's also interested in research problems around algorithms, graph theory, and combinatorics. Prior to joining IIIT Bangalore, she was a postdoctoral fellow at Institute of Mathematical Sciences, Chennai. So without further ado, we'll just call upon the speakers.
Good afternoon, everyone. My name is Jyotsna Bapat. I'll be talking about the spectrum allocation or the wireless portion of it and the difficulty of the problem and how graph theory was used to be able to solve this problem. The graph theory part of it obviously will be discussed by Professor Pradeesha. A quick background, today's talk is based on the work that we have done with our PhD student, Dr. Parthiban, and two of our IM Tech students, Rajat Rao and Divyanshi Rajput, along with Professor Pradeesha. And this was recently published in IEEE Wireless Communication Letters. So if you look at the title of our paper, it talks about perfect UE grouping for frequency sharing in full duplex cellular networks. So the perfect UE grouping part is where the graph theory is coming into the picture. And when I talk about the frequency sharing and full duplex, for the benefit of the audience, let me just quickly tell you about what exactly does full duplex mean. Most of us are familiar with the concept of simplex communication, duplex communication, half duplex, correct? The simple example of simplex communication is our TV remote. TV remote can communicate with the TV. The TV can't exactly communicate back with our TV remote. A half duplex communication is where both sides can communicate with each other, but not at the same time. This very simple version of it, when both sides are utilizing exactly the same channel, we have seen in the example with the walkie-talkies. After end of your communication, you say over, then other side starts speaking. In non-communication language, imagine the rail track on which only one train can go in one direction. Other train can go on the same tracks in other direction, but at another instance in time. Most of the times what we see is the half duplex communication, but it is out of band. That can be done in two ways. For example, in TDMA, when two sides are communicating, both are not transmitting or receiving at the same time. It is done fast enough so that for most purposes, we don't even realize that we are not transmitting always at the same time. Other option is where both the sides are communicating over two different bands. Again, imagine here your regular road on which the cars are going in two different lanes. Cars are traveling one in one direction, another one in other direction at the same time, but not in the same lane. They are in two different lanes. Versus a full duplex in-band communication means both the cars need to travel at the same time in the same lane, essentially. How do we actually manage to do that? And that's the question. If we manage to do it, obviously, we can double the number of cars that can be on the road at the same time, improve the capacity. So most contemporary communication system contain terminals that work as both, obviously, transmitter as well as the receivers. These terminals operate, as I said, in half duplex or out of band full duplex mode. In half duplex, transmission and receiving are the same frequency band, but at different times, also referred to as the TDMA. Other one, out of duplex, refers to transmitting and receiving over different frequency bands. If we allow them to communicate over the same frequency band at the same time, we can double our channel capacity. That's our fundamental idea. This has been happening. Earlier, it was only the half duplex communication. Later, we started using the hard duplex communication, but out of band. And this, the last one, is where we are leading. What is the problem there? The idea seems really simple, right? What could be the problem? Now, when you are transmitting, there is going to be some interference from the, when you're receiving, there is always going to be some interference from the signal that you are transmitting itself. If you see the first picture there, you're transmitting and receiving in two different frequency bands. The red one that you see, which is much shorter, that's your received signal. That is always weaker than the signal that you are transmitting. But because you are in two different frequency bands, the interference can be easily removed. Versus when you are transmitting and receiving over the same band, now you have a problem. You are receiving a signal which is going to be considerably weaker than the signal that you are transmitting. And most of the times what will happen is your own transmitted signal will overwhelm the signal that you are trying to receive. This is what I talked about before I changed my slides. I said that we want to increase the spectral efficiency. So in every which possible way we can increase, we are always looking for it. This particular technique which I talked about, in-band full duplex, in which again I'm going to repeat, I'm going to use the same band at the same time for transmission and reception. It has been used extremely successfully in wired communication. Remember, even when we used to make phone calls using our dial-up phones, there were no two wires. Over the same one, we used to transmit as well as receive. Why doesn't it work for wireless? What is so different that we couldn't really do it for wireless? Again, I gave reference of one of the authorities in wireless communication, Professor Andrea Goldsmith. There you can see that there has always been that for wireless systems, receiving and transmitting over the same frequency band is generally not considered feasible. People didn't even want to try it initially. What was the problem? Let's see. There is something called the self-interference, or when we are talking about the phone kind of a thing, it's the echo. So when I'm trying to listen, some of the signal that I'm transmitted comes back and also affects me, and that is nothing else but the echo. In the wired communication systems, there were two large signal processing algorithm systems that were used, what was called the echo cancellation. Why doesn't the echo cancellation work for wireless systems? There are two problems there. In the wireless system, my transmitted signal is going to be stronger, and more importantly, my received signal is much, much weaker than what we would have had in our wired systems. So a very simplistic analogy, this is equivalent to your saying that I'm trying to listen to somebody who is whispering. At the same time, I'm screaming on the top of my voice. Now what happens is most of the times what I end up hearing is my own screaming. Listening to somebody's whisper becomes a difficult thing. And this is what is referred to as the self-interference. Earlier, we used to call it the echo. So due to this presence of echo, implementing this in-band full duplex was considered extremely difficult. And even now, none of our wireless systems use that. We still use either two different frequencies, or we are going to transmit and receive at different times. Yes. It does. Yeah. So that's why we have.
And the received signal is much, much weaker than the.
In the wired systems, our received signal is not as weak as we have it in wireless. Typically, what we say is wired system is what is called a guided communication. So the way your waves are coming towards you, typically the received signal strength will be stronger. One of the examples that we had given is Imagine you are throwing a handful of rice to another person, and I have a pipe between us. I throw, say, 10 grains of rice. Out of 10, at least 9 will reach the other end. 10th one might come after some time after bouncing. It's guided medium, it will go this way. Versus in wireless, it's essentially like I'm throwing it up in the air, whichever way. So you might get a grain of rice, if that. So overall in wireless, your received signal strength will be significantly lower. That's the problem. And now I need to cancel that. And so that has been always been of interest. Like, can we still remove this self-interference so that very easily I can double my spectral efficiency? And this technique can be used on top of any other techniques that are present right now. So there have been several experiments. Two research groups, I have given you the reference there. They have looked at it and they said that, look, I can do this, of course, with considerable work. And when the difference between the transmitted and the received signal levels is up to 110 dB. Remember, dB is a logarithmic scale. So you are looking at 10 to the power of 11. That's the kind of difference between the transmitted and the received signal power. So it is potentially possible, but it's going to be extremely expensive. So because the difference is so large, what we can, typically the way it will be done is, there are 3 stages in which it happens. One is passive cancellation, in which I make sure my transmit antenna and receive antenna are far away. In a small phone kind of a thing, that's going to be difficult, but that could be one of the things. Then some of the cancellation is done in analog, some of the cancellation is done in digital domain. So if you do in these 3 steps, you may be able to capture the signal, which is 10 to the power 11, smaller than the signal that you are transmitting. So it is possible. Problem that will result in very expensive antennas, RF baseband structures. And because it will require some intensive processing, the energy consumption will also be higher. When I require more expensive hardware, I require more processing, more energy. That means your hardware is going to be expensive. And this will be required at both transceivers. Now imagine in our wireless scenario at the base station as well as the small handset that we have. Additional processing at the base station is generally acceptable because base station has the processing ability. They're also not limited by the battery power. They have the regular supply available. And you need one base station, you need thousands and thousands of user equipments or UE. Expensive UEs that are energy hungry, that's not an acceptable solution. So what people came up with is what is called the hybrid architecture. So in a hybrid architecture, your base station has the capability to cancel the self-interference. So it will be able to, it can do the processing and it can cancel it, versus your UE, user equipment, or your handphone doesn't need to change, it will remain exactly the same. So how is this going to work? And with this also, we will be able to double the spectral efficiency. So how does it work? Imagine this. This is your base station and this is the user equipment. Right now, both the transmission and reception is happening over the same frequency band. So now the processing has to be done at both base station and the UE end. In a hybrid architecture, now what is happening is whatever frequency at which one UE is transmitting uplink, uplink is from the UE to the base station, downlink is from the base station to the UE. That same frequency can be used by another user equipment for downlink. So what is happening? Any interference cancellation that has to be done at the base station, but at the user equipment end, they don't need to do any of the interference cancellation. Yes, I have a small table here. So typically with out-of-band duplex, what would happen is that I'm looking at a FDMA kind of an architecture here. User 1 uses frequency F1, for uplink, frequency F2 for downlink. User 2 is using F3 for uplink, F4 for downlink. With this hybrid architecture, the first user is still using different frequencies for uplink and downlink, but those same frequencies can be used by user 2 for downlink and uplink. So the user doesn't need to do any self-interference cancellation. However, the base station needs to do, and typically, as we always do, we say putting on the load on the base station is okay, because there's one base station and typically it has the processing power. That's the idea behind the hybrid network. Now, what is the problem here? User 1 is using frequency F1 for uplink, and user 2 is using it for downlink. As always, let's say your uplink signal, when you're transmitting, it is strong. By the time it reaches, it will be a weak signal. If UE1 and UE2, if they were close enough from each other, then the uplink signal of user 1 will interfere with the whatever UE2 is trying to receive from the base station. This is called the, remember we had the self interference. Now we have what is called the side link interference. I'm getting interference from other users. So how do we manage that? So now we have what is called the side link interference, because I'm sharing now the same frequency with another UE. So herein we say that, look, the signal strength decreases, and it decreases rapidly with distance. As the signal travels longer distance, it is going to be, oh yeah, you can use this. Yeah. It is going to decrease. So why not change two UEs which are sufficiently away from each other? So the idea is that pair only the UEs that are at a distance which is sufficiently apart, so that the side link interference is what we call at an acceptable level or below the noise floor. So I won't go over the two slides. These two slides, these are how we modeled the signal path loss. Depending upon typically what is the transmit signal strength and any of the antenna gains, what would be the received signal strength? And we have the channel models for the downlink from the base station to the UE, uplink from UE to the base station, and between the two UEs. So this work, I'll kind of won't talk about it. Okay. So now the idea is that the UEs that are going to share should be at a sufficient distance apart, so that the signal between them, it won't interfere with each other. The signal strength should go down. It should go down to an acceptable level or below the noise floor. So now based on this, in this case, we have considered a single cell OFDMA based hybrid network. And it consists of some N user equipments that are present, and there is only one base station, and R is the radius of my cell. It is assumed that the base station has the geographic location of each one of the UEs. And it is a fair assumption, as I've given this thing there, if the base station has the access to each one of the UE locations. Based on these locations, it calculates a matrix A, which consists of the Euclidean distance between the UEs. So D11, obviously, the diagonal elements will be all equal to 0. D12 is the distance between UE1 and UE2. And the matrix is going to be symmetric, because D12 will be equal to D21. And this is the distance matrix that is there. We use the distance matrix to prepare what is called another matrix, which is called the adjacency matrix. I'll talk about that. That's in the next slide. So this is the idea here. Now, in this case, there are 6 different user equipments that you can see. Out of this, the distances are such that the ones you show in that are shown in blue, they are grouped together. There's a set of 3 which has been grouped together, and they are sharing the frequencies amongst each other. The green, they are the group of 2, the pair that can share the frequencies, versus the red one is considered that it is close enough to all the UEs, so it cannot really share any frequencies. So 2 frequencies will have to be allocated for that one. So that's the idea here. Now with the 6 UEs, for example, here we would have needed 12 different frequency bands. Instead of that, we are going to use 3 plus 2 plus 2 here, or 7. So this adjacency matrix is derived such that if the distance that we had from the previous matrix A, if it is greater than a certain distance, which is d min, the minimum distance, which will make sure that the other signal goes to a level which is acceptable, correct? So, but then that element will be 1, otherwise the adjacency matrix will contain 0. Now, 2 UEs can share the frequency band if the distance between them is greater than d min, or in this adjacency matrix, Bij, which will be equal to Bji, is equal to 1. In our case, we have considered distance as the parameter. You can take different types of this thing. You can take some SNR threshold, for example, the received signal trend, RSRQ, or if you go to higher levels, the ACNAC reports. Different criteria can be chosen to see which of the user equipments can be paired together. Yeah. They're going to share the frequencies. Let's see if maybe this picture is. So if you see the picture A, here you have the, for example, you are seeing that what is on the right, let's say that is your uplink, what is on the left is the downlink. Just look at part A. So the same frequency can be used for uplink and downlink, uplink for one UE, downlink for other UE, and vice versa. And that is your one group. The same thing in the next one, B, there is a group of 3 in which now the green one is the uplink for one UE, it is downlink for other UE. Similarly with the color red, similarly with the color blue. Yeah.
Screens will be moving, right?
Right.
Which means that the grouping has to be done dynamically.
Correct.
And the second thing is that it is optimal. The algorithm will be optimal only if the UEs are far apart. If the UE is the Euclidean distance, we measure the Euclidean distance to separate out the groups. If they are very, very nearby, then this will not lead to any improvement in efficiency. Right?
Correct. So that's why the whole problem, I'll answer the second question first. The idea here is choosing the UEs that are far enough apart from each other. So if you have a cell there, you are aware of where everybody is, and then you choose the ones which are the furthest apart, or at least sufficient distance apart. So there will be some UEs which are close to each other, you will not be choosing those. And going back to your first question, absolutely, the UEs will be moving. We are saying that this update will be done every 1 millisecond. And we have also added one more change to our algorithm so that every time we don't need to do the allocation, it will be done incrementally only depending upon the UEs that have changed the position. So we have looked at the correlation between the adjacency matrices. Thank you. Yeah.
Just to clarify,
Huh?
so the left one, where you have n equals 2, right? Those two are sufficiently far apart.
Right. They will be paired only if they are far apart.
The group actually in that sense is ones that are far apart.
Right. Okay, this picture could have been better in that sense. No, this one. I should have shown those to be far apart.
But it's easier
Draw.
Just following the one.
Yeah.
Understanding that for every group,
Mm-hmm.
the pairwise distances between the UVs in that group must be above a certain threshold.
Correct.
That's what.
Correct.
And there should be 2 for every group that you form.
Need not be true. There you have 3. It can even be 4.
So,
Yeah. Huh.
Yeah.
No, I think here only adjacent. So 1, 2, 3 anyways. If you have a larger group, correct me.
Yeah.
So if you have like 1, 2, 1, 2, 3, 4, 5, 1 and 2 should be far apart, 2 and 2 should be far apart, 3 and 4 should be far apart because only they are sharing.
The groups can be, you can either have, you definitely need a group of 2 or group of 3. Okay. 4 users can also share frequencies amongst them, but you could also implement it, imagine it as 2 users sharing frequencies. But you definitely need 2 or 3. If I have 7 users, and let's say all of them are satisfying the distance relationship with at least one another user, then I can share, 2 can share, 2 can share, and 3 can share. Why do we need larger groups?
It can be a cycle.
It will be a cycle.
But why is it restricted to working?
I think that is only give you an example that it can be done into
It doesn't need, see, it's easier for us to have 2 and 3. However, I'll talk about something called the weighted grouping. That's where actually we really sought Professor Pradeesha's help, because we couldn't do it our own. When you do the weighted grouping, that's when you might have, you might do better with a group of 4 than with 2 groups of 2. Yeah, and there is also.
Power codes, even though you these are closer and you are sharing both the time and frequency among the code, there is some orthogonal cover codes or some sort of spatial beamforming. You can achieve this goal.
But you can do this on top of your spatial beamforming also. So any technique you use, this can be done on top of it to double your spectral efficiency. And if you just use orthogonal codes, that is going to add to the spatial this thing also.
The sharing the frequency. The transmission is in the form of data or noise, different risk.
It again, you know, right now it does, see, most of the times now, even whether it is voice over IP, any one of the communication, that won't really matter. Yeah. So this is how the sharing might happen. For example, let's say here, this is the triplet here. FS is used for the uplink for one user, downlink for the other, and so on. Okay, everybody roughly got the idea about how this has been done. So what is the goal of this again? To group or to, I'm avoiding using the word pair, because pair essentially means only 2. And the group can, because sometimes you're going to need 3 also. So group each UE with another UE or UEs in the cell such that maximum spectral efficiency can be achieved. You will get the maximum only when all the UEs are grouped with someone or the other. Larger the minimum distance that you use for pairing, so lower will be the grouping probability. If I increase the requirements for that, my grouping probability will go down. But when I increase the minimum distance, your side link interference will also be minimized. Challenges are, what could be the pairing criteria? We just use distance, but as I said, something better can be done. And determining these groups such that the spectral efficiency can be maximized. So I won't go into how these grouping algorithms are. We have had several publications on it. I'll list it towards the end. So in the first one, wherein we did the entire exhaustive search, wherein we found that theoretically the best set of UEs, groups of arbitrary size. And this required the exhaustive search, all the groups that are possible from all the sites. Just because you found everything with the pairs and the triplets, that doesn't cover it. You might do better with the larger group. Then we had proposed another reduced search algorithm wherein we will do the changes only depending upon using the UEs which are acceptable or which are suitable for sharing. That reduces overall our search space and the overall complexity. And then we also have another one which can be done much faster, wherein we limit it to only finding the pairs of 2 or 3. We are not looking at the larger sets. Okay, I'm going to say a few words about graph theory. Although somebody like Professor Pradeesha is also present here, I'm going it we're very much into the layman's terms here. So this is when we were doing the search. This is where we first we thought of using graph theory, because our search was depth first, breadth first, and that's when my student and I, we started reading it a little bit more. So the graph is essentially a pair of sets. You have the vertices and your edges. And any two vertices that are adjacent to each other, and we said that the edge is connecting the two. And the adjacency relationship between these vertices is captured by using the adjacency matrix. In the adjacency matrix will contain 1 when the adjacency requirements are met and 0 otherwise. Most of the wireless communication folks are familiar with this because we had used something called the graph coloring algorithm when we had looked at the allocation of frequencies across different sets. So in that case, the idea was that the color cannot be assigned to two adjacent vertices, but at the same time, the same color can be repeated as many times as possible. So when we were looking at the solution for this, that's what we thought about. I said, look, we have something similar problem. We don't want to reuse the frequencies when we are too close to each other. But we were different from this problem in one big way. In this case, for example, frequency F1 can be utilized as many times as possible. In our case, one frequency can only be used twice because it can be used once for uplink, once for downlink. It can't be used more than that. And our problem was different in that sense. So that's where we started looking at it from the graph theory point of view. And then we had modeled our hybrid network as an undirected graph. And this allowed us to find these user groups effectively, as we will talk next. I will talk about this and I'll show the results. And there was one more approach that we wanted to look at, which was called the weighted grouping. What do I mean by that? Initially, we had the condition that if the distance between the two UEs is greater than a d min, it's acceptable. But is that really a right thing to do? For example, two UEs might be considerable distance apart versus the other two UEs are just about d min distance apart. Shouldn't we be looking at it what we call the soft decision rather than the hard decision? And in this will reduce the side link interference even further. And we wanted to find such a solution without reducing the grouping efficiency. And that's what our latest work was about. When we searched it using the brute force search, it wasn't possible to compute it, versus using the perfect grouping algorithms from graph theory. Professor Pradeesha and her students were able to give us a complete solution for that. I'll quickly show you the results here. So the first graph there shows the CDF of the side link power. So by using the weighted grouping approach, you can see that the side link interference now is at the 95th percentile, it is now down by 2 dBm. From -95, it goes down to -97, which is significant for us. And the UE grouping efficiency, if you notice there, as the number of UEs start increasing, our efficiency starts going towards 100. That means we are getting closer and closer towards increasing the spectral efficiency to twice the value what it is supposed to be. And real quick, two more plots here. How do we determine what happens to the distance between the UEs? If you see the top two plots there, we are able to increase the distance between the UEs that are paired by using this approach. So overall, reduce what is called the side link interference. And we will show later looking at the complexity of these algorithms. They can be computed in polynomial time. So it is possible for the base station to be able to determine which ones can be utilized depending upon for each one of the cycle and pair them. And as the earlier question also said, it can be used along with any of the other existing techniques, whether you are beamforming any one of them, the same band, if it can be used by two different users, you get double the spectral efficiency. How the graph theory then was done, I'll hand it over to Professor Pradeesha. Thank you. Yeah. Right, hybrid. Hybrid was the base station had the duplexing capability. Versus our user equipment was normal. Thank you.
I'll continue there. I should warn you that there's a slight different, yeah, I'll be talking a slightly different type of, different language than Professor Jyotsna has been talking. So I'll just make sure that all of us are on the same page. Now, what happens to the problem when you ask it in a graph theoretic way, right? So Professor Jyotsna has already told about D-mean. So these are groups of size 2. These are groups of size 3. And there can be what we want to do is identify groups of possible, if possible, identify groups of larger size. Okay. And how does it look in a graph is, see, 1 and 2, they are very far apart, very far, the definition of being far, meaning they are more than d-mean away. So they in the graph, we add a edge between them. Professor Jyotsna has already explained it. And also 1 and 2, they are also sharing a frequency. The red one, whatever is what is depicted as depth one, they're able to share that frequency because they are far from each other. That means in the graph, there is an edge between them. And 2 to 3 also is sharing a frequency, the green color, which is represented by the green color. So there is an edge between 2 and 3 also. Similarly, 3 and 1, they are also sharing a frequency. So there is an edge between them. Okay. So when we talk, think of this as a graph, so we are given a graph where the vertices correspond to the UEs here, and the edges correspond to whether they are more than threshold d-mean away or not. And a group correspond to whether a group of size 2 correspond to 2 vertices which are connected by an edge. And a group of 3, size 3, correspond to this thing which we defined as a cycle of length 3. Now, if we have groups of size 4 or 5 or what we are essentially looking for are cycles of length 4 or whatever size. Okay. So now the question is, so I'll cycle is. But I'm not sure if, since we are using Euclidean distance, cycle, does it always correspond to maybe, but it might not be true. It depends on what you use for threshold, right? So you're only looking for a cycle. So only 2 adjacent vertices are sharing a frequency. So 1 and 2 is sharing a frequency, 2 and 3 is sharing a frequency, 3 and 4 is sharing a frequency, whereas 1 and 4 may not be sharing a frequency. So that way it is only a cycle.
We shouldn't have any edge other than the cycle edges. Right?
No, it can have other edges. It can have diagonals. It can have diagonals. We are not looking for induced cycles. That's it.
Cycle is optimal, right? There can be more than a cycle. And there is more than a cycle.
And more than one cycle, yes.
No, I mean, meaning that there can be a subset. A subset nodes with edges more than a cycle.
Yes, that is perfectly okay with us. We don't have an issue with this. We just want to have cycles. There may be diagonals, as Professor told. There can be diagonals. It can be a complete subgraph in it. That is also okay with us. That does not violate anything. The minimum condition that we need is a cycle. Right. Okay. Edges. Yes, that is a problem. We want to decompose or partition the vertex set into set of edges and set of cycles. There may be some other vertices which correspond to our the vertices which are not grouped, the UEs which are not grouped, and we want to. I'm sorry. No. In fact, it's a polynomial time. We have an algorithm for it. Okay.
So basically, cycle decomposition.
Cycles and matching. A decomposition into cycles and matching. Some vertices may be uncovered uncovered. The usual cycle covering problem in graph theory, try to optimize the number of cycles in some way. Here, what we are optimizing is the number of vertices which are not covered by cycle. That is a different. That's what we. So the cycle covering problem is NP hard, as you know. It's
Is the objective to increase the cycle length or minimize the number of unconnected nodes?
number of ungrouped, minimize the number of ungrouped vertices. So you can, yes. So you can have a number of groups of size 2 also, as long as everything. That is also fine. Okay. All right. So yeah, so I just want to introduce, I hope everybody in this room know what a matching is, but still, given a graph, a matching is a subset of edges such that every vertex is incident to at most one edge in that subset. Okay. Should I explain something? Okay. I'll give an example might be. So this is a graph. We have vertices 1, 2, 3, 4, 5, 6. And the edges are 1, 2, 2, 3, 3, 1, etc. So I take a subset like this, 1, 2, and 5, 6. This is a matching because this red edges, they do not share a vertex. Or in other words, equivalently, a vertex is part of at most one red edge, right? Like one is part of, the vertex 1 is part of one edge, 4 is part of no edge, 5 and 6 again part of one edge. So this is what we call as a matching in a graph. Okay. Then there is a concept called perfect matching in a graph. A perfect matching is a matching where every vertex is incident to exactly one edge. That in other words, you are covering, the matching covers all the vertices in some sense. So, okay, some other examples. So look at this graph, x1, x2, x3, y1, y2, y3, and we have all those edges. And if you take these black edges, they form a perfect matching. It's a matching because the edges do not share a vertex, and every vertex is part of some matching. The previous example was not a perfect matching. This is not a perfect matching because 4 and 3 are not part of any of the edges. Okay, so I have one more example, the same graph. Okay, the same graph, this is a perfect matching in the graph. Every vertex is part of an edge. Okay.
For every graph, does a perfect match exist?
No, there are graphs where perfect graphs do not, perfect matching do not exist. Okay. Trivially, if the number of vertices is odd, then you cannot have a matching at all. But that doesn't guarantee you have even number of vertices, does not guarantee a perfect matching again. Okay, right. So now weighted graphs, one more concept. Here we have a graph and we have a weight function on the edge set. That means every edge is assigned a weight. Okay. And this can be used to model a number of real world scenario. We'll see how. So Professor also told about how to use Euclidean distance when we represent UEs as graphs. Okay. So that we are going to use that. And bipartite graphs, another concept that we are going to use is it's a graph where the vertex set can be partitioned into two such that all the edges goes across the partition. Okay. So like this one, this is a bipartite graph, x1. So the bipartition here is x1, x2, x3 form a partition, and y1, y2, y3 forms the next part in the partition, and all the edges goes across. There is no edge from x1 to x2, for example. Right? And you can ask a matching question, or the question to find a matching in bipartite graph also. That's usually referred to as assignment problem. And bipartite graphs obviously has more structure than general graphs, and hence the matching problem admit more structural and better structural and algorithmic results in bipartite graphs also, which again is one thing that we are going to use in our algorithm. So, okay, and matching is in graph theory, matching is it's a very well studied problem. an area of study, and you will not believe in where all have what all applications have been found for matching. There are like conferences just talking about matching questions. Okay, so we'll just mention some of the questions, some of the very basic questions studied in matching. One obvious question, algorithmic question, is to given a graph, find a matching of maximum size. That means find a matching with the maximum number of edges in the matching. Okay, you can also ask, given a graph, whether it admits a perfect matching, whether there exists a perfect matching or not, and if yes, how to find it, etc. In weighted graphs, you can ask to find a matching of maximum total weight. You want to maximize the total weight of the edges that are part of matching. You can also ask, find a perfect matching of maximum total weight. Find a perfect matching that every vertex is part of a matching, and you want to find such a matching which maximizes the total weight. You can also ask the question of find a perfect matching of minimum total weight also. Okay. So one result that we are going to use is that the minimum weight perfect matching problem in bipartite graphs with n vertices can be solved in this much time. Yes, it's a quite old result in bipartite graphs. Okay, and in fact, the same algorithm with some modifications will also give you this result. If you want to maximize the size of the total weight of a perfect matching in bipartite graphs, even that can be computed in polynomial time. We are going to use these algorithms as a tool in the algorithms that are designed. Okay, right. So let's come back to the frequency allocation problem. This is the graph theoretic. This is how you ask the problem in graph theoretic form. So you're given a graph. The vertices in the graph corresponds to the UVs, and there is an edge between two vertices if the corresponding UVs are more than d min away, at least d min away. And what do you want to? You want to find groups of UVs that can share frequencies, which means, or which in graph, what you're looking for? You're looking for a matching, that is a set of edges, which again corresponds to groups of size 2, and a set of cycles. Every cycle is a group of size at least 3. And you want to find a matching and set of cycles such that they're vertex disjoint. Of course, the groups should be disjoint. And the total number of vertices that are not covered by this matching and set of cycles is minimized. That is, the number of ungrouped UVs are minimized. Every UV, or you want to maximize the number of UVs which are part of a cycle or a matching. So this is the problem that we are going to solve. Okay. And to solve this problem, what we do is we reduce this to a perfect matching question in bipartite graphs. So you are given a graph. Okay, so you are given this problem, unweighted maximum group problem, and you reduce it to a minimum weighted perfect matching problem in bipartite graphs. Okay, so that means you're given a graph which represents the UV and the frequency, the arrangement of UVs, and you reduce it to a bipartite graph, and you ask to find the minimum weighted perfect matching in that bipartite graph. Okay, and to solve this problem, we use the algorithms that we have mentioned earlier. So the non-trivial is.
How did we draw equivalence from there?
No, I'm just saying. Ready.
How did we jump?
Yeah, that's the non-trivial part. That's the non-trivial part, how to reduce this to this, because this graph is not even a bipartite graph, right? So you have to build a bipartite graph such that a minimum weighted perfect matching in that bipartite graph somehow corresponds to an unweighted maximum grouping in the original graph.
In graph theory, that if we have unweighted maximum grouping problem, you can recast it to this or reduce it to this. I just wanted to know the intuition to go from there to there. It's well established or something which you knew that we can reduce.
No. This is our contribution to the This is a novelty that we our algorithm has. Okay. But I should also mention that similar problems with cycle covering is that this technique is used, that converting it into a matching problem. Okay, so let's see the reduction. Yes.
Preference between just the matching and the cycle, like whenever
No.
you have a larger set,
No.
you would like to have that. Is that
No, right now there is no preference between the matching. There is no preference. So in the next question, we'll prefer groups where the distance is very large, but right now there is no preference about the size of the groups or the number of the groups or the distance between UEs in the group. Right now, nothing is there.
But I think that's because they result in the same efficiency, right? Use the same number of.
In terms of frequency, in the gain and frequency, it's the same, right? So if you have a number of, like you have a matching or you have cycles and matching or just cycles only, what matters is just the number of vertices covered by your cycle union matching.
Uncovered guys are the real.
Uncovered guys are the real problem. That's what we're.
so there's no preference, then why follow the
We might not get full gain. For example, a trivial example, if you take an odd cycle, suppose a graph is an odd cycle. Okay, whichever way you find a matching, there will be one vertex, which is in the cycle, you just take the cycle and you achieve. Okay, right. Okay, fine. Okay, so let's see how this reduction is done. Okay, so let's call the graph that is given to us as G, vertex at V and E. Okay, so first part, for every vertex in this, that is for every UA, we are going to build a new graph, G dash, which is going to be bipartite, right? So we will, for every vertex in the original graph, in the new graph, we create two corresponding vertices, Xi and Yi. Okay, and we are going to say that X1, all the Xi's and Yi's are going to form a bipartition of the graph. Okay, so yeah, so let's start with a very simple graph. Let's say this is the graph that we started with. And we have vertex 1. In the new graph, you build two vertices. Let's call it X1 and Y1. Similarly, for 2, you have two vertices, X2 and Y2. And for 3, you have two vertices, X3 and Y3. Okay, and this is going to be a bipartition. X1, X2, X3 is going, and Y1, Y2, Y3 is going to be a bipartition. Now we will add edges between Xi and Yi's. So you will add X1, Y1, X2, Y2, X3, Y3. Okay. So this is how we encode the vertices there. So far it's a bipartite graph. There are no. Yes. Okay. So we have these edges. I'm just going to call this horizontal edges, the green edges. Now, further, we have edges here, right? So we have the edge 1, 2 there. So there we have vertices X1, Y1 and X2, Y2. So when we have the edge 1, 2, we are going, in the new graph, we are going to add the edges X1, Y2 and X2, Y1. We are going to add this.
the intuition that one group represents receivers, other group represents transmitters. That's right.
Okay, so we add these for every edge here. We add two edges there, okay, between the corresponding X and Y's. Okay, so after this, so the full reduced graph is this. So you have 1, 3. So you add the vertices, edges X1, Y3 and X3, Y1 also. So this is, see, we get a bipartite graph. I didn't add any edge between X's or Y's. Okay, right. So this is the reduction. So this is my reduced graph, which is bipartite. Okay, so we'll have another, okay, I have to give weights also to them, right? I'm going to ask for weighted perfect matching. So for this green edges, the horizontal edges, the weight is going to be 2. And for the cross edges, no, is it? Oh, yeah. For the cross edges, the weight is going to be 1. Okay, right. That's it. So that's that's the new graph that I'm building from the original graph. Okay. Let's see one more example. So one graph here. So here, see, you have edge 4, 5. So I have 4 this edge and this edge, x5, y4 and x4, y5. Similarly for all this. Yes, because, yeah, just wait. I'm going to explain that. Because this is somehow, these edges, you want to reduce them in your matching. You're going to convert it to minimum weighted matching.
The minimum weighted.
Yes, all right. Minimum weighted. Okay, all right. So now let's see. Okay, now let's look at this graph. And I'm going to say this, that if there is a matching in G, I can find, okay, ignore the 2 direction, but I can find a matching in G dash. Okay, right. How? See, this is a matching in G, right? 1, 2 and 4, 5. I can find a small matching on the other side also. How? I have 1, 2, so I take these edges. So corresponding to 1, 2, I have 2 edges, 2 cross edges here, right? So I take them, x1, y2 and x2, y1. And with 4, 5, again I have 2 edges, so I take them. You can see that it's a matching. They are not sharing any vertex. So, okay, so if you have a matching here, I can find a matching here also, right?
It just eventually correspond to your standalone.
Ungrouped, that's going to be, right? Okay, right. And similarly, if I have a cycle here, 1, 2, 3 form a cycle, I can find a matching corresponding to that cycle also. How? See, 1, 2, so I have, okay, look at the cycle 1, 2, 3. I have the edge 1, 2, and I know that here I have this edge, x1, y2. I have added this. And now I have 2, 3. I take the edge x2, y3. Then 3, 1. So I take the edge x3, y1. This can be done for any cycle of any length. So I have cycle 1, 2, 3, 4, 5, 6. What I do is x1, I'll take x1, y2, x2, y3, x3, y4, and so on. And finally, I take xn, y1. I didn't repeat any vertex. So this is going to be a match.
Would this be always unique?
Yes, for every cycle. Okay, I can take the cycle in 2 directions. I can call it 1, 2, 3 or 3, 2, 1.
No, even in the same direction, 1, 2, 3.
Yes, if it is 1, 2, 3, I am telling you how to take the vertices, right? If you call it 1, 2, 3, then it is the edges I take is x1, y2, x2, y3, and x3, y1.
In the same. Yes.
So you fix your favorite ordering of your of the cycle and take the edges
In the same.
in the same order. Okay, right. So have cycle. If I have 2 disjoint cycle here, then also I have a matching here, right? And it's going to be a matching. Disjoint cycles, disjoint matchings. Total, it's another matching. Okay, right? So what we have seen that if there is a matching here, there is a matching here corresponding to that. If there's a cycle here, there's a matching here corresponding to that. Okay. Now I'm going to say that if there is a grouping here, then there is a perfect matching there. Okay. So let's look at okay, this is what we just said. Okay. Now let's look at a grouping. Okay. So my grouping is I've grouped 1, 2, 3 together, 4 and 5 together. 6 is a different. It's not optimal grouping, but just for the sake of understanding, take it. Okay. So you have 1, 2, 3. So I have this matching. See, when I consider x1, 2, 3, and I take x1, y2, x2, y3, etc., the vertices x1, x2, x3, and y1, y2, y3 are covered by the matching. Okay. Now I have this edge 4, 5. So I take the edges x5, y4, and x4, y5. Okay, so this x4, y4, x5, y5 are also covered by the matching. Okay, right? But I have this ungrouped vertex here, 6, right? And here I can see that x6, y6 is not covered by the matching so far. So what I do is I take this. I know that there is an edge x6, y6, and x6 and y6 both are not covered. So I take that. Okay. But what happened when I take that edge? What is the weight of that edge? 2. All the other edges that I've taken were cross edges. They are of weight 1. But for ungrouped vertices, I take this horizontal edge, which is of weight 2. So therefore, it is here. It's not very difficult to see that if I have a grouping here with there are k vertices, k UEs which are ungrouped in the graph G dash, I can find a perfect matching whose weight is n plus k, where n is the total number of vertices. Because for every ungrouped vertex, I am paying 1 more. Right? The weight of the edge in the matching is going to be 2. So I'm instead of 1, I'm adding 2. The reverse direction is also symmetric. I'm not going there. So you can see that if you have a perfect matching here with the weight n plus k, you can find a grouping here which where k vertices are ungrouped. Okay. So therefore, here, if you find the minimum weighted perfect matching here, you can find a corresponding grouping here. Okay. And you know that finding a minimum weighted perfect matching, there are algorithms are available for it. So you use that algorithm. So far, how much time have you spent? The reduction is almost linear in number of vertices and edges. And after that, so the time, the work that you do or the maximum time you spend is to find the minimum weighted perfect matching and put it back. So that gives us this result. So the unweighted maximum grouping problem, it can be solved in this time, n power 5/2 log n. Okay. So this is the algorithm and this. So the next question that Professor Jyotsna also asked is, so we know how to group. Okay, we know how to group vertices, how to group UEs, so that the maximum gain in frequency is achieved by sharing frequencies. But at the same time, we might be grouping vertices or UEs which are just threshold distance away, like just d min away from it. Whereas we will prefer it if the groups are such that the distance between the UEs that share a frequency is as far as possible. So far we haven't considered the distance. We have only used distance to decide whether it is less than the threshold or greater than the threshold, or equivalently whether there is an edge or not. Okay. Now I'm saying, okay, so for a graph, I know how to find a good grouping, but there may be many groupings, many good groupings. Okay. So I want to find good grouping where the distance is maximized. The distance where between UEs that share a frequency is maximized. Okay, right. So this gives us the next problem. You are again given a gated graph. You have to find a matching and a cycles such that the total number of vertices that are not covered by this matching and cycle is minimized. Right. So this is the frequency gain. And next, okay. So here you make this graph a weighted graph, right? So you decide the graph, decide whether the existence of an edge in the same way, that whether it is greater than a threshold or not. If it is greater than threshold, you add an edge and you give a weight to the edge, which is equal to the distance, the Euclidean distance between them. Right. Now, what do we need? We need to group the UEs such that, let's say 2 vertices are in the same group together, or in a group of 2, they are going to share frequencies. So, and their distance, or we should preferably group so that the distance sharing UEs are far apart. That is, if you have two solutions where the same number of UEs are covered by the groups, you want to return the one where the total distance between the UEs are maximized. Okay. So this is the next problem.
Sum of the weight.
Yes, sum of the weights.
So in this, for the horizontal edges will put 0 as the weight.
No. Not zero, but yeah, something similar to.
It's the same. I mean, for example, in that previous one, the bipartite graph profit matching problem, we try to minimize the overall.
Yes.
Here we maximize it.
Yes, but there is a catch, right? We have to optimize two things. We have to make sure that this is also satisfied, right? So there are two criteria that we want to optimize. We want to make sure that this is satisfied. Given this is satisfied, then we have to. So if we simply take a maximized matching or maximum perfect matching, what happens is the number of ungrouped vertices might get increased. Okay, right? So if it is just this, we know how to do it. That's what we explained. Okay. Now we say, okay, how to do this also after doing this, right? So I'll just give the intuition for this. See, the reduction is the same. You have the same graphs. The only difference is that how do we assign weights? Okay, so I'll just give the intuition why. It is clear that you want to increase the weights of this cross edges that you are taking, right? So in some way you want to take a maximum weighted matching, but at the same time you want to make sure that these ones are not, preferred, right? So what you do is, so I think Professor JSR already got the intuition, is that, so I give a value of minus delta there, where delta is large. It's the correct definition is there. But for the intuition, just say delta is large, therefore minus delta is very small. So you take, you give this value minus delta, and here it's the edge weights, which is the distance between them. Now you can see that if we have a matching of total weight T minus K delta, which delta is defined as before, then we have a vertex, we have a matching and a set of cycles such that K vertices are not covered, and the total weight of the edges here is T. And when you are maximizing this, you maximize T. There's some simple math behind it which will actually prove this. But the intuition again is this: you want to maximize the weight, so therefore you give this, and you call an algorithm to find the maximum perfect matching. But at the same time, you have to make sure that these edges are avoided as much as possible. So you keep their weight low.
You think data large enough so that.
Yes, you take that only if it is absolutely necessary. Yes. Yes, so that's it. Some function of total weights, something very large, that is it. It will not be sum of total weights plus 1 or something. Okay. So again, you use the algorithm. So here also reduction is not very difficult. But your time, you need time to solve the bipartite maximum weighted perfect matching problem, which will give you the. Okay. That's it. So yeah, these are the two algorithms that we have. So again, we have used concepts of free graph theory, or specifically the matching problem, to solve this problem. And it can be an effective tool in solving more complex problems also. And not only in communication networks, can also be used in robotics, social networks, transportation system, you name it. We have an application of graph theory there. Okay, that's it. And thanks for your attention. Thank you.
Yes. Any questions from the audience? Okay, I have two questions. Just a bit of trivia to the whole problem. The problem of full duplex was so hard for so long in communication that the first breakthrough was done by Professor Dinesh Bharadia, who is a IIT Kanpur alum. I had the fortune of meeting him in person. So he was awarded the IEEE Marconi Award in 2016 for having designed the first working full duplex radio. Of course, with the limitations of cost, complexity, and being able to do so much. So it was such a difficult problem for so long. So yeah, apart from the trivia, the question was, Professor Jyotsna, D-min plays a very crucial part, right? So what was the basis for choosing D-min?
So we looked at the receiver sensitivity. So we took the example of the picocell and we chose the D-min such that the received power there was below minus 95 dB.
Okay. So because
And-
I was just wondering if, you know, a comparison with something as dumb as this universal frequency reuse and looking at the D-min allocated on that dumb way of doing things
Right.
and such kind of a sophisticated scheme, that would perhaps give an idea about, you know, how much we are also able to achieve on the front of doing
Right.
things better.
Right. So we implemented this for picocell. Depending upon how larger your this thing is, our calculations of the transmit power and essentially the receiver sensitivity, we wanted to bring it below that.
Right.
So that it is essentially treated as the noise. Otherwise, we are raising up the noise floor.
Right.
And that's why by using the weighted graph, this thing, we were able to bring that down to minus 97. So it goes further below
Thank you.
by
Yeah,
using.
thank
Thank you.
Uh-huh. Definitely, if we very low for very high frequencies, and then it is expected to be higher for low frequencies, right?
For
For
low
example, 26
frequencies, yeah.
gigahertz or 40, you know,
So
47
that will
gigahertz.
depend upon your channel model and how the signal energy is reducing with distance.
And also because of the spatial direction of the higher frequencies, your D-min is expected to be lower, right?
Yeah.
I mean, I'm just thinking aloud, right? So, for example, in the recent 5G specification release 18 or whatever it is, so if they do a lot of frequency hopping, right, from 700 megahertz to 26, and they keep doing that, then this D-min will have to just vary quite a bit dynamically, right?
Right. So actually, just about when we're completing this, we had started getting questions about, how is this going to work out whenever you have the directed beam and how will you reuse that? That is something we need to look a little bit deeper into it. What we did though was we looked at 3 different cell size scenarios, and the larger the cell, the better is your frequency reuse, and our efficiency tends towards 100 as your cell size starts becoming smaller and smaller. But still, most of the times your efficiency was still above 90%. Yeah.
Is there an incremental version of this? Like, for example, suppose some UVs.
Oh, yes, we thought about it. Yes. We thought about it. We don't have a solution, but I think dynamic matching is it's a well-studied problem. So one option is how to incorporate that into this. So instead of recomputing it at every microseconds.
So that's why I was asking.
Yes.
Because you described to me it's not.
This is a static algorithm.
So that the onus was on the distant side wherein we update the distances as needed, and then the correlation with that, and with the solution will give a right away a solution.